In Chapter 14, Section 2, we're going to do some calculations with equilibrium reactions. One of those is going to be the equilibrium constant, or KEQ. And this is going to relate the concentrations of our reactants to our products. So this is a general equation. The capital letters represent the different types of substances, and then the lowercase letters represent what their coefficients would be. So to write an equilibrium expression, you would set KEQ equal to the concentration of the products divided by the concentration of the reactants. That's what the brackets stand for: concentration, which would be molarity, or moles per liter. And then you raise those to whatever coefficient there are. So if this were a 1, you wouldn't obviously have to do anything, but if it were 2, you'd have to square this value. If it were 3, you'd have to cube it, and so on. So you multiply the products and divide them by the reactants that are multiplied together. So this is just a real equation instead to show you how this is set up. So here, when we write our equilibrium expression, we're not doing a calculation, we're just setting it up. We're going to take the concentration of the NO2, which is our first product, and it has a 4 coefficient, so we have to raise it to the 4th power. Then we're multiplying that by our second product, which is oxygen, and we put it in brackets to represent the molarity. And then since it does not have a coefficient, that's just an implied 1, so we don't have to worry about it. Then we're going to divide it by our reactant, which is N2O5, so we put that in brackets for its molarity, and its 2 coefficient then becomes a 2 exponent. So here's a sample problem. This one tells us that we have a 1 liter vessel containing 1.6 moles of ammonia, 0.8 moles of nitrogen, and 1.2 moles of hydrogen. Calculate KEQ. And we're already given the balanced equation. So the first thing we need to do is to go through and find the concentrations, because that's what's going to go into our equation. And this one made it pretty easy for us. It told us moles and that it's all in a 1 liter container. So moles divided by liters would be the same as how many moles it would have. So our ammonia is 1.6, our nitrogen is 0.8, and our molarity for our hydrogen is 1.2. Now that's not always the case. Sometimes you're already given molarity, and then other times they'll give you a volume that's not necessarily 1. So just make sure that you calculate those out first. Then we're going to set up our equilibrium expression. So in this case, KEQ is going to be equal to the ammonia concentration squared. Okay, that was our product, and then our 2 reactants are the nitrogen and the hydrogen, and we're going to have to cube the hydrogen. And then we're just going to plug our values in. So we want to plug in our ammonia molarity, and then divide that by our nitrogen and hydrogen molarities, making sure that we square our ammonia and cube our hydrogen. And the value that we come out with at the end is 1.85. And since that value is greater than 1, that means that our forward reaction is favored. If it were less than 1, then that means the reverse reaction would be favored. The next calculation we'll be doing is called the solubility product constant, and that is going to be KSP. So this is our expression that we're writing for a solid ionic substance that is in equilibrium with its saturated solution. A low KSP means that it has a low solubility, and then a high KSP means it's very soluble. So in these types of problems, we've got our solid ionic compound, and then it's split into its 2 ions. And when we write out our KSP expression, we are only doing our products here. We do not divide by our reactant the way we do with equilibrium. So we're going to take the concentration of the calcium 2+ ion and cube it, and multiply that by our phosphate ion and square it because of its coefficient. So we'll only ever be using products, and only those that are aqueous and gases. If they're solids or liquids, their concentrations don't change throughout the equilibrium, so they will not go into these equations. So here's a sample problem with solubility. It says to calculate the KSP for a 1.34 times 10 to the negative 5th molar saturated solution of AgCl, and we're given our balanced equation. So what we know here is our molarity for this silver chloride, and that's it. And in our equilibrium expression, we need the concentrations of both of our products. So this down here is just a little proof. You don't necessarily have to show me this, but if we were to have this molarity, then that means that's how many moles per liter we would have. and then if I set up my mole ratio here from silver chloride to silver, that would be the same value. And if I did the same with the chlorine, it would be the same value because they're all in a 1-to-1 ratio. So therefore, whatever this original silver chloride concentration is, will also be the concentration for the silver ion and the chlorine ion that it splits into. So when I write my equation, I'm going to do the KSP is equal to the concentration of the silver plus ion times the chlorine minus ion. Those are my aqueous products. And then I'm going to plug in 1.34 times 10 to the negative fifth for both of these values. And in this case, I just squared it instead of multiplying it by itself. And that will give me my KSP value for silver chloride, or it will tell me how soluble it is. Now this one here is not a 1-to-1 ratio, so it's a little bit different of a step that you have to take. So this one asks us to calculate KSP for a 6.54 times 10 to the negative fifth molar saturated solution of silver chromate. And it shows us our solid silver chromate splitting into 2 silver ions and a chromate 2 minus ion. So our KSP expression is the concentration of the silver plus squared times the concentration of the chromate. Now, since we are given the concentration of our solid, and this is in a 1-to-1 ratio with the chromate ion, then this original concentration is also going to be the chromate's concentration, so 6.54 times 10 to the negative fifth. Now with the silver, this is a 1-to-2 ratio, so I'm going to have to multiply this concentration by 2 and plug it into my equation, and then still square it, because that's part of my original KSP expression. If this were a 3 coefficient, I'd multiply it by 3 and then cube it. It's whatever that coefficient is. Plug all that into your calculator and you get 1.2 times 10 to the negative 12th. The last thing that I want to discuss is the common ion effect, which is the reduction in the solubility of an ionic compound by the addition of an ion in common with it. So for instance, here I've got a silver chloride solution going on. I've got silver chloride breaking into silver plus and chlorine minus ions. Now if I already have this equilibrium system going and then I were to add some NaCl, that means that not as much of this silver chloride would be able to stay dissolved. In fact, some of it could even potentially precipitate back out into the solid form because this sodium chloride has a chlorine ion in common. So that will cause this to not be as soluble. The same thing could happen if I put in silver nitrate. It would have a silver ion in common, so some of this would not be able to dissolve as much as it could if it were by itself.